Okay, this is a problem on page 301. If you'll look at the back of chapter 5, you'll notice that there are a lot of problems, and most of them don't have a description. The reason for that is these are all just beam problems. And generally what we're trying to do is figure out the loads within the beams. That's what we care about, because we're interested in the stress and how much load the beam's carrying. So let's start off with figure 5-4. So this would be problem 4, basically, in the book. Now you guys probably know how to solve these problems, but we'll go through them as sort of a review. Now how much beams have you done before? A lot or a little? Sort of. I did mixed answers. Okay, well then we should be able to go through these quickly and not have too much trouble with them. So help me out here. Let's see, there's several different potential problem statements. Keep the reactions at the supports, of course we always have to do that. Determine the magnitude and location for the maximum and absolute value of shearing, force, and bending moment, and also basically make shear and moment diagram. We're going to do all of that, but mainly we just want to find out the loads throughout the beam and what the maximums are. So let's start. I'll copy the figures for this because I think that'll be helpful. The author seems to be indicating reactions with the arrows with lines through them like this. And there's 3 foot here, 8 foot here, 3 foot here, and then he's got 10K, and I'm pretty sure what he means by that is 10,000 pounds, so 10 kips essentially. Page 301. All right, so the first thing to do is to calculate reactions. Let's call this A, let's call this B. Of course, this is simple. Now, in the procedure in the text, the author recommends 2 moment equations and then check with sum of forces. I'll do that. It's probably a good idea, so I'll go through and do that. But this shouldn't take us too long. Now, each of these distances are feet, so let's start off with some moments at A. Take this direction positive. Sum is 0. What do we have? Well, let's see, there'd be a negative 10 times 3. Notice I'm not going to write in the units because it would just be thousands of pounds times feet. Okay, so that takes care of the first one. What's the moment arm for the next 10K load? 11 feet, because it's 3 plus 8. Good. So 10 times 11, that's also a negative moment. And then the positive moment is going to come from B. So let's just say R sub B. Let's see, yeah, that's consistent. Multiplied by the moment arm, which is 3 plus 8 plus 6. So that is 14. Okay, so now calculate RB. This should be straightforward. We just move these to the other side. I'm going to do several steps at once. Plus 110 divided by 14. So this is easy, right? Because this 30 and 110 is 140. Divided by 14 is just 10. If I did all of that right, the reaction here should be 10,000. So 10K. That means the reaction at A is going to be 10K. Okay, we could go through in some moments on the other side, but you see this is a mirror image. There's no point. We add 10 plus 10, that equals 10 plus 10, so life's good. Okay, that's not all of it. That's just the reactions. Now we want the shear and the moment. Now, I'm going to make something a little bit clearer. Normally, and this is pretty standard, normally what you do when you're talking about the shear and the moment loads within the beam, you cut the beam and you leave what's on the left-hand side. So it gives you a sign convention. I'll show you what that is quickly. So here's A. Let's say we cut it after the 10K load, somewhere along this 8-foot section. Okay. Any shearing that is down in this direction is considered positive. Any moment in the counterclockwise direction is considered a positive moment. That's just a sign convention that you've probably seen before. Just about everybody uses it. Okay. That's when you're on the left side. It gets confusing when you're on the right side, but for now this is fine. Okay, so we'd like to draw the shear along the length of the beam. So let's see. Let me, if I do that here, my body will be in the way. So let me go ahead and basically just copy the beam over here. So we have A here, we'll have the 10K load here, the other 10K load, and the reaction at B here, bless you. Okay, so, and I should have, I tell you, whoops, let me move the beam over because we're going to need more space than that. Okay, so let's just try one more time. 10K and then B. All right, now to get the shear diagram, now we're going to take this direction to be positive shear, and it will be in thousands of pounds. So your author is just using K for that. I'll stick with it. Okay, as we go along, the shear begins, well, let's see. If we're cutting the beam, let's think carefully. If we're cutting the beam here, do we have to orient the shear this way or this way to keep the little segment in equilibrium? It would have to be down, right? Because this force is up. So that's a positive shear, okay? So we'll go to a positive shear of 10K, okay? That will be constant until we get here. Then what happens? Well, this load of 10K means that if we cut the beam after, well, there's 10K here, we don't have to apply any shear load, right? This segment can be in equilibrium as far as the Y direction goes without any load. So let's see, or without any shear, excuse me. So that would go back down to 0. So the shear goes down to 0. Okay, fine. Now, what happens next? Well, as we move along, eventually we get to the point where this is the free body. Okay, we've cut the beam over here. Now do we need shear up or shear down? Up. That's a negative thing, right? It's not a very good shear arrow. That's better. Because look, we got 20K this way, 10K this way, we'll have to apply 10K of shear this way. But that is a negative shear. And so on the shear diagram, it should look like this. So it comes along, goes down to, and now I'll be careful, a negative 10K. Now the check we get is at the end, this should go back to 0, and it does. Okay, because that load we know is 10K, and it'll take us back to the axis. Okay, now let's make the moment diagram. The moment diagram is pretty straightforward. Positive moments, and this will be in K feet, so thousands of pounds times feet. Positive moments, let's go back and consider this. Positive moments, those are the things you live for in life, right? Bad joke. All right, so the shear is down. What's that going to do? That's going to tend to rotate the whole thing in this direction, so we have to apply a moment like this, or at least in the material. The material has to apply a moment to keep that little section from rotating, right? So we've got to apply a twist this way to prevent the shear and reaction couple from causing it to rotate clockwise. Make sense? So the moment initially is a positive moment. Now, when you cut the beam just barely to the right of this load, the moment is 0. Okay? As you get more and more length of the beam, the moment has to increase because the moment arm of the shear increases. And so as you guys probably remember, we're just adding an area. You don't have any area initially. You add more and more and more, and you get more and more moments. So it's going to be a linear increase because this is just a constant value of shear. So we add the same amount as we move along 1 foot at a time, for example. Okay, so we'll come up to here. What is the value of that moment? Well, let's see. We got 3 times 10. Yes, it's 30. So 30,000 foot-pounds would be the moment. Does that make sense? What happens to the moment here since the shear is 0? Nothing. It remains constant because understand the shear diagram tells you how the moment diagram changes. We don't add any area, but we don't subtract any. So the moment just remains constant. Does that make sense? Okay. So then we get to this point, and now we're adding negative area. That means that we'll make the moment go down. And so there we go. And sure enough, the check is, do we end up back at 0? Well, again, 30 times 10, 3 times 10 would take us back down to a 0 moment. So there's the shear in the moment diagram. Now, where is this beam going to fail? Well, usually beams fail due to moments, not due to shears. So anywhere in the central section, you could say it's going to fail. However, to me, the most important points are here and here. Why? Because not only is the moment highest there, the shears are highest there as well. Okay? So the 2 places where I would worry about this beam failing would be at those 2 points. Questions? Comments? So the maximum value of moment, 30,000 foot-pounds. Maximum value of shear, 10,000 pounds. Okay? Was that easy or hard? Too quick, too slow?